All right, let's do multi-threading. In part one, we're going to discuss something called a race condition. Now, a little background. What we've been doing so far is just single-threaded code. We did this all through 380 and so far through this engine as well. We visualize our program as just a series of instructions that you do one after the other, one instruction at a time. So for example, maybe we'll update some game objects, we're going to run some AI or something, and then we'll update the animation. Okay, we did the blending and the posing, we did all that. Maybe there's some physics to do some collision raycasts, we'll do, separate the boxes, whatever. And then we'll draw everything. Now that we've decided where everything is in the world, we go through and we send those off to the GPU. So we do have, two things going on, only because we have the GPU rasterizing triangles while we're preparing those draw commands for the next buffer. But nowadays, the power of the computer has really accelerated, not so much in making the instructions faster, but recently by cramming more cores onto those machines. What does that mean? What is a core? Well, here's a typical diagram for what a CPU core might be. Now we have something called the instruction pipeline. We haven't really discussed that in this class. That's a little bit out of scope of what I want to cover. But we did talk about these assembly language instructions. And the instructions don't really happen in one clock cycle of the chip. It takes several clock cycles to complete the instruction. But modern CPUs are pipelined, meaning it does parts of each instruction per clock cycle, so that it can be working on one instruction and then move that instruction to the next stage while it starts up the next one. And so the instructions, we imagine it going through a pipeline in the system. What it means is it takes more than one cycle to complete any single instruction, but because they're flowing through constantly, the number of instructions per second is dramatically improved by that. Okay, so that's the instruction pipeline. And then we've got some registers. We talked about those, the AX, the BX, the MM0, all those registers, floating point registers, integer registers, SIMD registers, vector registers. And then this blue box here represents, that's the actual working guts of the computer. That's where the adders, all the math, ALU, arithmetic logic unit. So that's where we do the math, that kind of thing. That all goes in this big box here. And then over here we have a cache bolted right on, kissing right up next to all of this hardware as close as possible for fast data access, your primary cache sitting right there. All right, well, turns out that a big part of the bottleneck in all of this is that instruction pipeline. As it turns out, a lot of that execution hardware, there are things, adding, multiplying, math operations, logic operations, all those wires, I'll call them wires, transistors on the chip, mostly sit idle while we're in the pipeline. They are active at different stages of the pipeline and for different instructions. So what the real bottleneck is accessing registers and the instruction pipeline itself. So what they have done in modern CPUs is introduce the concept of hyper-threading. Now, a hyper-threaded core has a pair of these things, has a pair of registers for each execution unit and cache block. That allows it to run two totally separate instructions through the pipeline as long as they're not fighting over the exact same execution bit or the exact same L1 cache access. Because it's already pipelined, you can get almost twice as many instructions through this architecture as you could through a single one. And that allows us to run as if we had two cores, almost. I tend to call it at least a 50% speed boost, probably more, depending on what you're running. It just completely depends on what you're running. So that's hyperthreading. As the hardware gets more and more complicated, we've started bolting on whole new cores, like the complete another CPU. Like, here's my CPU, it's even a hyper-threaded CPU, it's got a cache on it, it's got registers, instructions, everything. How do I make my computer faster? Just give me another one. I'll take two computers and I'll cram them into the same box. And so that's what this diagram is here. We now have two CPU cores, and each one is hyper-threaded, so we can run 4 programs on this machine at the same time. Okay, so that's what we're talking about here. How to make use of all those extra programs that we can run simultaneously. Okay, how we do it is with something called threads. Let's imagine this scenario here. For example, let's say I have a procedure, we'll call it proc A, that does something slow. Let's imagine that that is a slow function call. Don't know what it is, who knows. And I'm going to run 3 of them simultaneously, right? I have 4, on this chip, I have 4 cores I can run at the same time, 4 threads I can run at the same time. So I'll use 3 of them to run that slow procedure. And then I'll use the 4th one to run my main. And that's what that is. So the idea here is that this function run in new thread that's a proxy for take this other program that I'm giving you, this one, and send it off to another thread to run on that other thread. So we send that one off to a thread, send that one off to a thread, send that one off to a thread, and they'll all go simultaneously. So now all I need to do on the last thread, the one that started it all, is wait for everything to finish. And I'm all clever. I'm like, how do I know when those other threads are done? I'll tell you what, I'll use a global variable, and I'll just increase that global variable each time one of those threads completes. And once it hits 3, then I know I'm done. Okay, it's a good time to point out a keyword you probably have not seen before: volatile. A volatile int says that it's the key to the compiler that tells that compiler this integer might change in a way you can't see. Think of it in terms of like old school controllers. Old school controllers were literally wired into the machine. It was a bit or a byte that could change when the user pressed the button. So if we have like a bit somewhere in the hardware that just changes when the user presses the button, the compiler has no way to predict when that's going to happen. So we see it here on the main thread in this while loop. There's no way that the GA variable can change during this while loop. So if you don't put the keyword volatile in there, the compiler is likely to optimize that out and say, that's just while true. There's no reason to check GA because I know that GA is not going to ever be less than 3, or not after the first run at least. And since the first run happens right here, the compiler would not see that GA could change, but we know that GA could change on another thread. So that's what volatile tells it. Okay, so it says arg on the top, and it says, what's the problem with this? What's wrong with this? This looks fine. What is wrong with it? What happens when 2 of the 3 threads run this instruction at the exact same moment? What happens? Race conditions. That's what we call race conditions. A race condition is any time when multiple threads executing code could happen either AB or BA, and you don't really have any way to control the order in which the threads execute their individual code. Okay. When does this come up? Anytime we have a shared resource that multiple threads are accessing, this can happen. What do I mean by that? We had, in the previous slide, we had a global variable. A global variable that is being shared by all four in that case threads. All four threads are accessing that same variable. And 3 of those threads are changing it, and the other thread is reading it. So it's impossible to predict exactly what order those 3 threads are going to do their thing. And we'll see in the following slides how very badly that can go. So let's do a little exercise I like to call Be the Computer. We have assembled here, this is the assembly code for that instruction. This one instruction in C++ compiles out to the sequence of 3 instructions in assembly. So let's first take a look at what those say, and then let's be the computer and go through those instructions one at a time. First, we move from an address into the register EAX. This is the address, evidently, of the GA global variable. So we're going to just load from whatever's in GA now, put that in a register. Next instruction, add 1 to EAX. So that's the plus plus. So just increase EAX by 1. And then here we have a move from EAX back into that memory address. So store the answer back in the global variable for the next person who wants it. Simple. So that's plus plus GA as assembly. Now let's be the computer and execute these steps one by one. So first, when I run this first instruction, what do? I want to move from this address into there. Now, it's not on the slide, but it's actually right here. It starts off as 0. So I'm going to move the 0 into the EAX register. The EAX register now contains a 0. All right, next instruction. That was easy. Next instruction. Add 1 to EAX. EAX will become 1. 0 plus 1, that's 1. What happens to this memory address? Nothing. We don't touch it, so we'll leave that one alone. There you go. Let's do this third instruction right here. We're going to move from EAX into that memory address. So EAX is going to go into there. So we've got a 1. And EAX is not modified, so let's fill that chart out. So there we go. That's what we should have ended up with. That is what the computer does step by step. Okay, now let's talk about how that can become a race condition. What happens if there are 2 threads doing the same instructions at the same time? What we'll do here with this little chart is, since we only have one brain to work with, let's imagine we are doing time slicing. So we'll run a couple of instructions here on thread number 2, and then we'll run some instructions on thread number 1, and then we'll come back and wrap it up on thread number 2. Okay, it's the same instructions we already did. Here we go. Be the computer. On thread 2, what do we do with the first instruction? We read in from the address into the EAX. So that's a 0. Goes in there. And thread 1 is just idle. We don't know what's going on there. So next, thread 2 gets another instruction. It's going to add 1 to EAX. So that's 1 goes there. Nobody modifies the memory address, so that'll stay 0. And now we context switch. Now we switch over to this to thread number 1. Thread number 1 kicks in now, and it does the first instruction. The first instruction, move from the address into EAX. Well, the address still has a still has a 0 in there. And so we'll move that in, and thread 2 would not be modified by that. So we'll just fill that in. Next instruction, again on thread 1, we're going to add 1 to thread 1's EAX. So thread 1 is right there. I'm going to add 1 to its register, and we will not modify the memory, and thread 2 isn't doing anything, so it's going to stay the same as it is. Okay, now we're going to stay on thread 1, and we're going to do the last instruction of thread 1, which is to move from EAX into memory. So EAX holds a 1. We'll put that in the memory, and we will not modify what's going on with thread 2. All right, and then finally we will kick back to thread 2 to execute this last instruction. We're going to, from EAX, move that into the memory. So this is thread 2's EAX, goes into the memory right there, does not modify the value, and of course thread 1 is not modified. So there you go. We finished our program on 2 threads, and this is our answer. So, so what? So what's the problem? If we back up and try to understand what we were just trying to do there, I think you might realize what we just did is to say 1 plus 1 equals 1, right? We said plus 1 here, plus 1 here, and the answer is here. And the reason that happened is because of the way this thread interrupted this other thread. Because it interrupted what it was in the middle of doing, it totally destroyed the work that was intended. And this only happens because of the specific timing of when that happened. If thread 1 had kicked in 1 cycle later, if it had kicked in just 1 instruction later, there would not have been a problem. But because it injected right at that moment, that's how we got the problem. And that's why it's a race condition, because the 2 threads are racing, and we can't predict which thread is going to come first. All right, that's it for part 1. Let's circle back around and come back for part 2, where we'll talk about how to deal with race conditions.